Alright guys, we're going to talk about heats of reaction in this video, meaning the heat that's involved in a chemical reaction. So far we've only been looking at phase changes and things changing their temperature, but we haven't looked at actual chemical reactions. So the first thing we're going to look at are called enthalpy diagrams, and if you remember, enthalpy means heat. So an enthalpy diagram basically kind of diagrams what's happening in the reaction. And you can see up here we have the reactants, and down here we have the products, and you can see that this many kilojoules is being released from the reactants to the products. So this is considered an exothermic reaction. The heat is being released to the surroundings. So if we look at it in terms of a balanced equation, you can see here are our reactants, here's our product, just like we had up in the diagram. And then we're showing here that the enthalpy is part of the products. That means it's being released from the system. It is being given off. So anytime you see the kilojoules in the product side, that represents an exothermic reaction, just like having a negative delta H, just like the heat going from reactants and being released as the reaction continues. All of those things represent an exothermic reaction. Okay. Now, if we look at an endothermic reaction, okay, the opposite is true. The reactants are gaining heat. Okay, so you can see here's our reactants. They're gaining heat to make the products. Okay, so in our balanced equation, the heat this time is on the reactant side. So 27 kilojoules is being absorbed by the system in order to make the products. Okay, so in an endothermic process, the delta H is a positive number, as you can see here. Heat is going into the system, and then our kilojoules would be over here on the reactant side. Now, when we look at these thermochemical equations, basically what that means is a balanced chemical equation that includes the physical states and the energy. That's what we were just seeing, the energy being in the reactants or being in the product side. And if we specifically look at combustion reactions, then we have a heat of combustion. And you can see here there's a lot of different things. It gives their formula, it gives what the actual heat of combustion is, and you'll see here that it's in kilojoules per mole. Now all of these are negative delta H's, which means combustion is an exothermic process, which makes sense. When things burn, when things combust, they're giving off heat. That seems to make sense. Okay, so here's our example. It says to write the thermochemical equation for the combustion of glucose. And of course, as you can see, I've made a mistake here. So instead of this being H2O, that should be 6O2. Obviously, combustion is something plus O2 yields CO2 and H2O. So here's the combustion of glucose. Now, to make it a thermochemical equation, we need to include the heat involved. So if you look at the chart that was given, we can see that the heat for the combustion of glucose is 2,808 kilojoules per mole. Okay, well, how many moles of glucose do we have? Well, if we look at our coefficient, how many moles of glucose do we have? We have 1. So that means to write our thermochemical equation, we're going to include the 2,808 kilojoules as one of the products because it's an exothermic process. It is giving off that many kilojoules for every 1 mole of C6H12O6. Alright, and then we can use that as a conversion factor. Because it's in our balanced equation, we can basically use it kind of like in a mole ratio. So if we want to know how much heat is evolved when 54 grams of glucose is burned, we're going to use our conversion factors. So we start exactly like we always start with our mass over 1, whatever's given over 1. Now, in our balanced equation, you'll notice that the kilojoules are per mole. So we're going to have to convert our grams to moles. So the molar mass of glucose from the periodic table is 180.156 grams. So our grams cancel, okay? And then from our chemical equation that we just wrote, we know that 2,808 kilojoules are released for every 1 mole of glucose. Okay, so we use it kind of like a mole ratio with our kilojoules and our coefficients from our balanced equation. So when we get our answer with 3 sig figs, we are going to create 842 kilojoules in this particular reaction.